Welcome to this video. This is the third video. I think the video was about performance, measuring performance, explaining and defining performance measurement metrics for applications like tracking. For example, aeroplane tracking. I think I defined the scenarios in the first video. In the second video, I think some categories of the tracking and performance measurements. So in this video, I think I will define more on the algorithm free. Yeah, the performance measurement categories, sensor related and tracker related. And tracker related performance measurements can be algorithm free and algorithm dependent. So here I will be working on the algorithm free measurements. I think different type of performance measurements for tracking applications that does not depend on the algorithm, and defining those, right? Let's see. So cardinality measures, yeah, some numeric based on some numbers, cardinality measures. So it is tracker dependent. That means that we are estimating the tracks. The true targets are there, sensor measurements are there, and we're estimating the trackers path of the targets, and this metrics related to a tracker when you're actually tracking it, creating the paths. Sometimes we don't create the paths, we just based on sensor measurements we define the performance measurements and all those things. So yeah, I think in this case, in many cases, true target informations are there likely, but it does not have to be. Okay, that's my understanding up to this point. Usually, for the simulation software, yes, we have the true targets we measure, and many measurements will be based on the true targets, true target positions, and true target trajectories, velocities on those. Anyway, so algorithm free, it does not depend on the particular algorithm. We can apply it overall. Yeah, it can also be applied on the algorithm specific cases. Anyway, so what are the different algorithm free measurements? Cardinality measurements, count of valid tracks, false tracks, missed tracks, spurious tracks, completeness, broken tracks, swaps in tracks. Yeah, we'll be measuring how our tracking algorithm are tracking performance depending on those on these numbers. We have to find out this type of numbers, and then yeah, that will indicate some sort of performance. Yeah, we'll be comparing it with the actual number of valid tracks or yeah, actual number of targets, those kind of things. But in general, let's say define what does count of valid tracks in mean. Okay, a track is valid when a track is assigned to a target. For one target, there is one target is assigned to a track, and it is kind of following the true target positions. It can be far, but yeah, so it's a valid track. False tracks, let's say false tracks, it's not really following any aeroplane or following any targets. So what it is giving false tracks, I think it can be just from the false alarms, right? It can be from the false alarms. So false alarms are coming in a sequence. You're thinking, okay, this is a track, this is a target trajectory, but it's not a real valid track. No target is following the track. That's a false track. Okay, missed tracks. Missed tracks. Okay, let's say you have 3 targets. Now you could find one valid track. So you missed 2 different targets. So you missed 2 tracks. So your algorithm, yeah, is successful in 33% cases. Yeah, that kind of thing. Spurious tracks. Spurious tracks. Let's see. Yep, estimated track. You are thinking, okay, you are following just one target. However, your tracks actually mixes up to different target paths and gives one track, or multiple different targets, multiple different aeroplanes in one track. you are assigning multiple different targets, multiple different aeroplanes into one projected trajectory. So that is spurious tracks. Completeness. Completeness, whether you could successfully track a target from start to end. Let's say in your field of vision, in your area, the target was there for 30 minutes, but you could track it for 15 minutes. And another 15 minutes, you don't know where it is, but it was there. So it was, you could not completely track, right? So I think number of successful completeness, unsuccessful completeness, so those kind of measures can be some sort of algorithm-free cardinality measures. Broken tracks. Broken tracks, let's say, you could track it for first 10 minutes, and then you could track it for 5 minutes, and then you could again track it for the next 15 to 25 minutes. So yeah, you are not consistent in your tracking, breaking, I think, broken tracks. Okay, so a count of broken tracks in relation to the actual number of tracks, those kind of measurements, count of broken tracks, a particular scenario, yeah, that can be one cardinality measures. Swaps in tracks. So it can happen when multiple targets crosses each other's paths. So yeah, there are some swaps. So I think at the swapping point, you might be mistaken one trajectory for another, one target for another. Let's say you're following a target 1, target 2, they're coming to a point. Now, from that point, you're probably thinking that target 2 point is related to target 1. You are just showing them as a one tracks, and target 2 tracks is combined with the target 1. You're following the one track. So that is swapping. So I think swaps, I think number of, in terms of actual counting, yeah, number of valid tracks and number of swaps. So there will be some sort of calculation based on that. That's a coordinating measures for swaps in tracks. So 356, 407. Yeah, I'll go a little more. Yeah, I'm trying to do it in 10 minutes slots. So algorithm free time measurement. I think these performance measurements are based on time. Performance based on time measurements. The rate of false alarm. Okay, per unit time, how many false alarm are there? Or how many false tracks are there? Per unit time, how many false tracks are there? Redundant track ratio. Redundant track, let's say, redundant means extra, right? So there is, let's say, for target 1 track, you are assigning 2 tracks into target 1 or 3 tracks into target 1. So yeah, so redundant track ratio, I can say 3 instead of 1, or let's say there are 2 tracks, 2 targets, but you are calculating 6 tracks, 6 divided by 2. So that can be redundant track ratio, redundant track, okay. So probability of detection, probability of detection, I think it is a time measurement, right? As it is time measurement, I think what we'll be doing, I think duration of the track, divided by last scan minus first scan. Yeah, time between your last scan and first scan. On the numerator side, you will have the probability, duration of the track. This gives the probability of detection. Okay, it is, to the best of my knowledge, will be per track, per target. Fragmentation rate, how the tracks are being fragmented. Track latency, I think it is latency, confirmation latency. I think, let's say you are thinking, okay, this is the track, but before you confirm, you probably will check it for some time. So yeah, the time that you took to confirm, okay, this is a track for this target, that is the completion latency. And the termination latency, let's say the target has disappeared from your field of vision, but you are still thinking the target is there, you are still creating the track, estimating the track But after some time, you will see, okay, no, the target is not there. Then you will declare, okay, this track is gone, so delete it. So the time the target disappeared and the time it took to decide, okay, the target disappeared, this is the termination latency. So let's see, algorithm free. Some cardinality measures, it depends on the availability, available truths, truth to track association, truth to track association. Okay, let's say this is one kind of performance measurement. What we do it here is, let's see, you have the truth, true target positions, and you have the track there, right? So you will be defining a matrix. You will be creating a matrix. Let's say on the row side, you can see, you can keep the Monte Carlo iterations, the first iteration, second iteration, third iteration of your algorithm. And for each iteration and for each scan, so how many truth you were able to associate with the track. I think you are tracking, but whether you could assign the truth to the track successfully or not, it is just the count. Okay, I did not read the details about it. From the little bit of description I read, it looks like that's the most likely case, and that's what it is. Let's see. Yeah, you'll be creating an association matrix for which iteration and for which scan, I think for which iteration and for the corresponding scans were you able to successfully map truth to the corresponding track, and how many of them. Yes. So yeah, on the row side, row by row, that will be Monte Carlo iteration. On the column side, the corresponding scan and the count of successful truth to track association. Yeah, take a look into it. That is what I could find out, or with the little description what I read. That's my best guess, and it's highly likely it will be something this or very close. Anyway, I think it's 412, 356. So